Okay, so today we will start off in chapter 7, 7.1, dealing with inverse functions. So a bit of a review on inverse function topic probably covered in different math courses throughout your math career. And then we'll introduce kind of how the derivative and how to calculate the derivative of an inverse without having to actually calculate the inverse function, saving us some work, right? So first, some background info. What is an inverse function? So let's just kind of look at different representations of functions, right? So we can think of it really abstractly if we think of, let's say, right, this represents kind of our domain D. Domain D, right? And made up of our input variables called x, right? So we have 0, 1, 2, 3, etc. Maybe it's finite, maybe it's infinite, right? Those are just some sample values in the domain. Right. Set D domain, and then there's some function f, right? It performs some operation on the input x, and then the output is our function f of x called our range 6. Again, let's say these get mapped on here, and again there may be infinite other values here. Range, right? So D for domain and the set R for the range. Right, so we can think of it as a mapping from one set onto another. All right, now this idea of an inverse function, all right, so abstractly here when we think, all right, an inverse function, this is an inverse function. Okay, so here, the idea here is, let's say that this function that we define here is actually the function f of x equals to 3 times x. All right, so here we could see, kind of checks out here, 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, etc. Okay, so that would be our inverse function. The idea of, that's our function f of x that we define. The idea of an inverse is that we have the function x run through the function f, and out the other end, the result is 3 times x. So now the idea is that you take this element now in the set R, right, the range, and that gets pushed through another function, which we define the f inverse of x, and at the end, the result, I get back x. Right, now for a very simplified function here, 3x, a very linear, straightforward function, we could see right away to undo that, I can essentially just guess what the inverse has to be. To get back x, f inverse of x, if I'm multiplying by 3, the inverse of x would have to be x over 3. Right, so that's kind of abstractly when we think of an inverse, what exactly this means, right? This machine f that does something to the function, the inverse essentially undoes what initially was done to it. Now, graphically, all right, what you see here is the graph of two functions, right? Now, graphically, they are inverses if they are reflections across the identity line, y is equal to x, right? So what you see there, that dotted line, is the line y is equal to x. All right, and you can see if you think of this as a piece of paper, you would have folded along that line, those would kind of overlap each other. All right, so that is graphically the representation of an inverse function. Okay, so let's kind of define here in a bit more rigorous terms here. So I'll define here if we're given a function f, its inverse, and again, if it exists. All right, so not all functions are guaranteed to have an inverse, and we'll talk about in a second what are the conditions that need to be met for the existence of an inverse. If it exists is a function f inverse such that whenever y is equal to f of x, then f inverse of y is equal to x. So it's just putting more formally the operations that we did above here when we talked about, all right, from some set D into some set R. All right. So if we think of our initial function here, here y equals to f of x. All right. X is some element in a set D. The set D is the domain. And y, which is equal to f of x, is element of some set R. All right, so the set R is the range. Now on the other end here, when we have this, we say, okay, so in this case, when we flip this around, we have our set y is now equal to, or excuse me, what am I doing here? Excuse me. Y is now an element of the set R, right? And then f inverse of y, which is x, is an element in the set D. Okay, so essentially what happens is that the domain and range the sets get flipped around in this case for the inverse to set R, this is now the domain of the function, and now this is the range. All right. So another kind of notation we can use here for f, we could say, all right, f is a function where we take elements in the set D and then they get mapped onto elements in the set R. Where for the inverse takes elements in the set R and they get mapped onto the set D. All right, so this kind of flipping of the domain and the range from one set into another. Okay. All right, now some properties of the inverse. Okay, so properties of the inverse. So in terms of composition, so given f of x and f inverse of x, we have this, and then f inverse of f of x is equal to x. Okay, so we're given f of x and the inverse, f inverse of y. Again, we switch the domain and range around. This is what the composition of the functions would be. All right. Now, when do we have the existence of an inverse? All right. So as it turns out, in order for f of x to have an inverse, so f of x needs to be one to one for existence of an inverse. Okay, now if you recall from kind of a pre-calculus or any other algebra course, we defined a function to be that each input had exactly one output. All right, now the outputs did not have to be unique for each input, right? A different input could be mapped onto the same output, right? Think of the constant function. Excuse me, maybe y is equal to 3, right? All values of x get mapped onto 3, and that still made it a function, all right? Now, in other words, when f of x is a function, is that it passed graphically if it passes the vertical line test. Right, so for example here, if we had something like this, every vertical line hit it at most one point on the graph. All right, and if you had something that was like this, we could see here that it fails the vertical line test. Okay, so that is for f of x to meet the qualifications that it is a function. So now, in order for it to be a one-to-one function, it must first be a function. So it must pass the vertical line test, but a one-to-one function. One function is a function. So f is one-to-one. On a domain D, if each value of f of x corresponds to exactly one value of x in D. All right, so in other words, algebraically, what this means that f of x1 does not equal to f of x2 whenever x1 does not equal to x2. All right, and these values x1, x2 are just any elements in the domain. All right, so to kind of unpack this graphically, what this means is that it needs to pass the horizontal line test. Okay, so before, the vertical line test told us that this was a function. So this is definitely a function. All right, but if we draw a horizontal line, we see that it touches it at 2 points. All right, and in order for it to be one-to-one, what that definition is saying is that it must only touch the graph at most in one place. So while this is in fact a function, it is not a one-to-one function. Okay, so a one-to-one function would have a look of maybe something like our basic cubic function, where it looks something like this. All right, where we see, all right, definitely a function, passes the vertical line test. But it's also a one-to-one function, right? If we look at all of the horizontal lines, or not all of them, the infinite amount, but just we could see that really any horizontal line that we draw would only touch the graph at exactly one point. Okay, so this is a function, and it is also a one-to-one function. Okay. Now, if a function does start off to be not one-to-one, so for example, the function that we see up here, that one that is a quadratic type function, has a parabolic shape, right? Now, if we take the domain to be all reals, it is not one-to-one, but we can restrict the domain to make one-to-one. So for example, let me bring up a graph here. So here, notice here, if I remove any kind of restriction, so we have our graph of a parabola, y is equal to x squared. Not one-to-one, but again, if we make the restriction here where the domain is all values x greater than 0, right, then we can see, all right, now that makes it a one-to-one function. All right, and that's not the only way I can restrict the domain. We can say, all right, x less than 0. That would be also another interval where it is one-to-one, right? On that interval, where I restrict the domain, that will be a one-to-one function. Okay, so keep in mind that there are, for most functions, there are restrictions you can make that will make this a one-to-one function. Okay, so let's take a look at, let's look at an example here. So restrict the domain to make f of x equal to 2x squared minus x to the fourth, a one-to-one function. Okay. All right. So now let's take a look. Well, first, let's look at the graph of this, right? Probably the easiest way to figure this out is let's generate a graph. So let's look at 2x squared minus x to the fourth. Okay. Okay, so we see we have this inverted kind of W shape here. All right, and we could see that it is not one-to-one, right? All right, what we could see if we just graph here. Right, there's one line, right? And here we could see there, right? Definitely not one-to-one. Hits it more than once. But it is a function, right? If you think any right, if we think of any kind of vertical line, right, then it hits it at most once. So it is definitely a function. It's just not one-to-one. But I can restrict the domain here. We can, here's some points of interest here, right? Or we could say, all right, well, what if I restrict the domain right? So there are actually, as you can see here, several different ways we can do this, right? What if I only take into account values that are in the domain here that are less than -1? So let's say, all right, what if I just make x less than -1? And there you go, right? We have a a one-to-one function. Okay, and again, that's not the only restriction we can do. We can do, all right, what if I make x between -1 and 0? And that also makes it one-to-one, right? And we can also do, looking at here, all right, well, we can go from, notice any interval between -1 and 1, right, cannot include negative values and positive values, because then that wouldn't work out here, right? So we can go from 0, between 0 and 1, and again, that works out as well. Okay, that's one-to-one, and we can simply say, all right, just make x be greater than 1. And that also checks out, right? Excuse me. Okay, so there are several different ways, and within those, you can pick any subinterval. Like, let's say I want x to be between 2 and 3. And that also checks out as well. The intervals that I showed you here are simply just the largest intervals that we have. So going back to our notes here, one way to do this, we could say, all right, we could define D to be the set x greater than or equal to 1. All right, and that is just one interval. So now on this domain, f is one-to-one. Okay. All right. Okay, so now we know what are the qualifications, or what needs to happen for it to be an inverse. Okay, so here to kind of summarize here. Existence of inverse functions. All right, we say let f be a one-to-one function on a domain D with a range R. Okay, and capital D, capital R are just sets of real numbers. Then f has a unique inverse, so there is only one inverse. F inverse with domain R and range D. So again, we flip around the domain and the range such that and is equal to y, where x is an element of the set D and y is an element of the set R. All right. Now, in certain cases, they may be all real numbers, but it doesn't have to be. D and R do not necessarily have to be all of the real numbers. Okay, so here, so now moving along here. So let's look at, so now we defined the inverse, the necessary, excuse me, I forgot about conditions for the existence of an inverse.